Hi guys, in this video we continue by looking at bonding molecular orbitals by looking at the two types of bonding molecular orbitals required to be known at the Unit 1 level. Previously, we looked at covalent bonding by redefining what it means, where instead of considering a covalent bond as only the sharing of unpaired valence electrons between two nonmetal atoms, we go further to establish that a covalent bond is formed by the overlapping of atomic orbitals. When atomic orbitals overlap, a molecular orbital is formed. Let's look at two types of molecular orbitals. One which is called the sigma bond and the other is called the pi bond. On this slide, we see a definition of what is a sigma bond, where this sigma bond, also called a sigma molecular orbital, is formed by what is called end-on overlap of atomic orbitals, where through this end-on overlap of these atomic orbitals, we say that there is a maximum overlap along this internuclear axis. What is the internuclear axis? It is a line which joins the two nuclei. Because of this end-on overlap of the atomic orbitals, we say that the electron density, electron cloud, is distributed symmetrically about the axis. This is our definition of a sigma bond. Let's go directly to look at how, in the overlap of atomic orbitals, to form this sigma molecular orbital. We're going to look at how the overlap occurs, and we will see that the electron density is distributed symmetrically about this internuclear axis. Let us look at the atomic orbitals which overlap to give a sigma bond. We will start by looking at two s atomic orbitals. Two s orbitals can overlap about the internuclear axis, and from their overlap we see a sigma molecular orbital is formed. The reason why it's called a sigma bond is because of the electron density which is distributed along the internuclear axis. We will look at the three ways in which a sigma bond can be formed, meaning we're going to look at the three sets of atomic orbitals which lead to the formation of a sigma bond, and then we're going to go on to draw these diagrams so you can see it a little more clearly. So this is one way in which a sigma bond can be formed: overlap of two s atomic orbitals. Two p orbitals, that is two px orbitals, can overlap end-on. That end-on overlap will give us electron density which is distributed about that internuclear axis. So overlap of two px orbitals also gives us a sigma bond. An s orbital and a px orbital can also overlap to give us a sigma bond. We're going to continue by actually drawing what the overlap between the orbitals should look like. we say that a sigma bond is formed by end-on overlap. What does end-on overlap mean? This end-on overlap represents a maximum overlap between the atomic orbitals. So I'm going to draw my s orbital plus another s orbital. The overlap of these two s orbitals gives rise to a sigma bond. Right? They overlap along this internuclear axis. We can also have an overlap with an s orbital. And I'm going to call this a px orbital. Where the overlap occurs along what we call this internuclear axis. And this is why we say the electron density is distributed about the internuclear axis. And last but not least, we can also have two p orbitals overlapping. Now the p orbitals must overlap, as stated before, along this internuclear axis. Once they overlap along this internuclear axis, meaning that it creates what we call maximum overlap, the molecular orbital which is formed is called a sigma bond. What I'm going to draw into my three diagrams is the rest of the axes associated with my s orbital. So these are our three diagrams which show an SS, SP, and two p orbitals which overlap end-on to give us electron density which is symmetrical about this internuclear axis. One thing to note, where we have two different atomic orbitals mixing, such as this sp overlap, we say that the type of orbital which is formed is called a hybrid orbital. So for now, I'll just introduce the term hybridization, and hybridization refers to the mixing of different atomic orbitals. For example, s and p. We will look at hybridization in more detail later on. So just to point out one more note on my page is that when these two atomic orbitals overlap, they each provide a single unpaired electron to form a sigma bond, also called a sigma molecular orbital. And the electron pair that is contained in the sigma bond, we can refer to the electrons as sigma electrons. So this is sigma bonds. So we've looked at the formation of sigma bonds. Let's look at pi bonds or pi molecular orbitals. On this page, we see a pi bond, also called a pi molecular orbital, where a pi bond is formed by the sideways overlap of two p orbitals. As seen in the diagram, we have some sideways overlap of our 2p z orbitals, and we see that the molecular orbital formed shows electron density above and below the internuclear axis. This electron density distributed above and below the internuclear axis is considered to be asymmetrical. When we say asymmetrical, this means it is not evenly distributed about that internuclear axis. So there would be a node, and a node represents an area where there will be zero electron density. We're going to look at the significance of this sideways overlap, which results in electron density, which is asymmetrical. I'm taking a look at the slide on the screen where we have our internuclear axis defined on our diagram. We see the extent of that sideways overlap, and as stated, it says the p atomic orbitals through sideways overlap about this internuclear axis forms a pi bond, such that the electron density is not symmetrical about the axis, but it occurs above and below the axis. On this page, you're going to see a few notes written about the definition of a pi bond. And it also mentions where the electron density in the pi bond is found. So what I'm going to do is just draw a diagram showing the formation of our pi bond. And all we need to show is this sideways overlap. And of course, to draw in our internuclear axis. We're going to end off the video by discussing the strength of the sigma bond compared to the strength of the pi bond. Now, as mentioned before, where a molecular orbital is formed, the greater the extent of the overlap, the stronger the covalent bond. This would tell us the strength of the pi bond would be greater than that of the sigma bond. And this is because there is a greater extent of overlap in the formation of a sigma bond, and this is true end-on overlap, versus the pi bond where we have sideways overlap. And these are the two molecular orbitals we need to know about, sigma and pi bonds.